right, well, let's get started. This is our November, our monthly series, AI4C, Artificial Intelligence for Clinicians. And we are, this is presented by the Mass General Brigham Data Science Office, and we're delighted to have Dr. Judy Gichoya with us today to talk about her fascinating research and incredible paper that was published on Hidden in Plain Sight, an update to the Reading Race project. Again, remember that these series are every second Thursday of the month at noon, and we're scheduled September to June. We take July and August off for the summer months for folks to have vacations. And you can see we've had a wonderful fall lineup. You can see some of our previous speakers. We had Dr. Chuck Kahn from the Radiology Artificial Intelligence Journal and University of Pennsylvania. We had Sin Ho Do, our own Sin Ho Do from Mass General. And today we have Dr. Gichoya from Emory. And then for December, we have Omar Arno, who is a neurosurgeon. He's going to talk to us about his work. We'll have in January, George Shih from Weill Cornell Medicine. And in February, Elliot Siegel from the University of Maryland. And then we have folks beyond that in the spring. For those who are interested, you can actually go and view, give us a couple days to get it up online, but you can view the recorded sessions. You can do that by going to our data science office website. The URL is datascience.massgeneralbrigham, all one word there, data science, one word, massgeneralbrigham, one word.org. And you can get access to the educational activities on the website, which are at the top here, and then click on Artificial Intelligence for Clinicians, and you'll get access to those recordings. Again, Mass General Brigham Data Science Office .org. And again, please email us with any questions. And we do ask you to please complete the survey. We'll have that in the chat box, but that helps us to make modifications. We also have a presence on LinkedIn and Twitter, and you can barcode if you want to watch our AI4C recordings at any time. But today, again, we are delighted to have Dr. Judy Gichoya join us. Dr. Gichoya received her medical degree from Moi University in Kenya, and then she completed her medical internship at Kiambu District Hospital. She then got a Master's of Science in Health Informatics from Indiana University, Purdue University in Indianapolis. Then she did postdoctoral training in informatics at Regenstrief Institute in Indianapolis, and followed that a residency in diagnostic radiology at Indiana University, and then a fellowship in interventional radiology, which she did at Oregon Health Sciences University at Portland, Oregon. She's currently an assistant professor at Emory University, and she's an interventionalist. She does clinical work also, as well as an informaticist. She's also a member of the Cancer Prevention and Control Program at Winship Cancer Institute. She's been funded through a number of places, the Grand Challenges in Canada, the National Institute of Biomedical Imaging and Bioengineering, the National Science Foundation through the Electrical Communications and Cyber Systems programs. She's seconded to the National Institutes of Health as a data scholar, where she's been helping, she's a champion for open science, and she's been very involved with their open data science platform, a component that's in Africa, an initiative to harness data science for health in Africa. And in fact, she just returned from a trip to Africa. So maybe if there's time, she'll share a little bit about what's going on there. Her career has focused, and I've known her since she was very young and very active. And in her very young career, she's been incredibly productive. She's focusing really now on validating machine learning models for health in real clinical settings, exploring explainability of machine learning models, fairness, and a special focus on how algorithms go ahead and fail. She's worked on curation of data sets for SIM, which is the Society for Imaging Informatics in Medicine. She's worked on hackathons there, a machine learning committee, competitions. She's also helped with the American College of Radiology and the Radiological Society in North America, machine learning activities there, supporting the AI ecosystem to advance development and the use of AI in medicine. She's currently working on socio-technical context for AI explainability for radiology, especially looking at the dimension of human factors that govern perceptions and preferences of explainable AI systems. So very popular, very interesting and perplexing topic we're going to hear today from Dr. Gichoya. And the title of her talk is Hidden in Plain Sight. You're going to be fascinated by this. An update to the Reading Race project. So Judy, I'll stop sharing and you go ahead and share your slides and we'll take questions at the end. Remember to go ahead and put your questions into the chat. So Judy, please.
Thanks, Kathy. And I don't know what I'm going to do so that you can shorten that introduction. Despite many requests, they seem to fall on deaf ears. Again, thank you for the invitation. And it's really an absolute pleasure to be discussing some of our work. And, you know, I will go into detail about what the Reading Race project is, and also giving you a sense of where the future, what I think the future is in terms of this space of hidden signals. And I will end with a call that that if this is your lane or you know someone working in this space, that you should connect them to me and our group. Because like Kathy said, that we believe in this concept of village mentoring and hive learning, where no one is really an expert and we work together to really change the outcomes of our patients and do better research this way. So I'm not going to spend too much time. These are my disclosures, really described a lot in the introduction. So I'm going to talk about, review these use cases where AI has superhuman abilities to detect patterns like self-reported race. And then I'm going to discuss the possible mechanisms and explanations for this performance. And then finally, to maybe challenge you to think about the open research questions that will I think harness this ability for better performing models. So I start off with this picture, and this is just a trend of medical imaging in the US healthcare systems. And in Canada, this is work done between 2000 and 2016. And all I'm just saying is that there's quite a lot of imaging that happens every year. Millions and millions of images are acquired every year, but they're acquired for very specific reasons. For example, the emergency room doctor may evaluate for chest pain, abdominal pain, but there's this potential for if they contain some hidden information that's not perceptible to the human eye, that is for the radiologist, that to rethink this in terms of what it means to fetch this information and share it, and or figure out what it means for our patients. So I think you've heard everyone say this, a picture is worth more than 1,000 words. Apparently this appeared in the 1913 newspaper advertisement, and it turns out that in radiology, it's still the same. So earlier this year, we published, rather mid this year, we published this paper, which is the AI recognition of patient race in medical imaging. And this, if you look at the preprint, which had been there for months, and we got a lot of feedback, we ended up just calling this the Reading Race project. And so in this work, we will start off on just defining what a self-reported race is, because this can be a long debate. And here it's really how you see yourself and how others see you in the context of legal and social environment. So for example, if you're applying for a passport or a visa, and this is a mandatory field, then you will select a box. And if maybe you go somewhere else and I have to enter a field, then I may see you, like say, see Judy as Black. So this has nothing, the self-reported race as used in this paper has nothing to do with ancestry or genomic explanations, or because I think one of the things that came up from this work is that maybe that we showed that maybe race is a biological concept, and we know that that's a slippery slope, especially in the context of systemic racism. And so Why would you study something like this? It turned out actually it was an accident. And, you know, 2 years ago, there was the Journal of American College of Radiology was looking for papers on equity and what we ended up, you know, I had attended a datathon that I realized that people are not using one public chest X-ray data set. And I said to myself, wow, maybe our group had been doing quite a bit of work merging the clinical and the imaging data. And so I was very excited to just say, hey, why don't we look at the performance of these models for just the usual chest X-ray pathology prediction, but with the lens of equity. And, you know, as you start off your paper, I don't know if you do it like myself, but usually I'll be like, oh, why are we doing this? Like, what lesson do we want? And our hypothesis at that point was, hey, if we train these models or had more diverse data sets, it would eliminate the bias. I can tell you that is still very, very, very far from getting done. And it's this concept, just because you include people does not mean that you eliminate bias with them. And that's what we ended up finding, that when we brought them the models that would show, yeah, they have underdiagnosis for Black and Hispanic patients, they still performed maybe to a less magnitude of bias, but the patterns persisted. And so in this quest, as we were finding out why was this pattern persisting, we then started finding that these deep learning models are able to detect self-reported race from the medical images. Ended up testing this across multiple modalities, and I'll show you this, with very surprisingly good performance. And then started figuring out like the why. And we know that deep learning models are notorious for confounders, for example, body habitus and disease distribution. And so we explore that, and then further went into sort of like the mechanism of things of image manipulation or some other theories to explain, to try and understand why this happens. So we worked with multiple data sets, public and private data sets, and we worked with the MIMIC data set, the Chest Expert data set, the Emory Chest X-ray data set. You can see all this. The Emory has quite a lot of patients. This is the 2-year Emory data set. We're currently curating a 15-year Chest X-ray data set. And then we also had the National Lung Screening Trial chest CTs and the RESPECT chest CT, which is a PE study, and also an Emory chest CT dataset. This was not as much, but there's also Digital Hand Atlas. This is a public dataset. We have an Embed, which is the Emory mammogram dataset. This is actually available in the public domain, and the cervical spine dataset. This is just like a dataset that we had because we couldn't believe this was happening. What I've noticed is that we have quite a wide variation of patients in these data sets. And you can see for Black patients, you know, they can be as little as around 5% in Chest Expert to as many as 47% in Emory data set. And so there's a lot of variation, standards, split data set. And then, so the first theory we had was, well, maybe these models are learning from, by the way, I have a baby, so you will hear some assisted presentation. I apologize for that in advance. And so, the first theory we had was that maybe it's the model itself, the architecture itself. So we ended up mixing a lot of architectures, including the ResNet 34, DenseNet 121, and the FisherNet, and then moved on. Once we saw this performance was still very good on the chest X-ray models, we said, well, maybe it's something about the chest X-rays, maybe the contour. Why don't we move on to another modality, for example, breast or limbs or cervical spine, imaging. And so this is sort of like how we kept evolving. Obviously when you write the paper, it almost looks like you had this perfect idea, but it really was a labor of love to close to 2 years. And so the surprising thing, we found that the performance, the AUC for the chest X-ray self-reported risk prediction was above 0.96. And I usually explain that this performance is not like you've been fine-tuning the model for a long time. This performance occurs maybe around the second or the third epoch. And, we have early stopping for these models. And what's been surprising, it's like the validation dream of AI, that if I bring the model to MGH, that it's just going to work out of the box without fine tuning. And this model was never fine tuned. Every time we went to a new data set, we would find that the external validation was very good. I will have to say that the one place we had a lot of international colleagues, and they tested it on a Chinese data set, a Taiwanese data set, and a Japanese data set. And the one place where the performance was the worst was actually on the Japanese patients, where it was almost like 0.23, very what we would expect. And unfortunately, this was a small data set, and we've not been able to also localize the why. But everyone else who's subsequently gone back and looked at this, and other papers that have subsequently looked at their own work, they find pretty high performance, not just for race, but other demographics. We moved on to the CTs, and you see, a slight drop in performance. I want to say, yeah, this is not a task that radiologists usually perform. And so when we think about if it's not a task that the radiologists usually perform, what would be their performance? Then when we tried from the 6 radiologists on the group, it was very random. It's around 0.5 to 0.55. When you're reading chest x-rays, you're not thinking, this is from a Black patient or an Asian patient or a white patient. And so I mentioned that we had multiple architectures, and this was not the reason why this was happening. And so there's quite a lot of work done about the saliency maps are not very useful when you change the order of the data that you're training, when you change the labels. I mean, they're so sensitive to subtle things. And I just put this here because if you don't show some images and saliency maps, people feel like you've not done a thorough job with computer vision. And I do have to say, one of the most, my group is not an expert in this, but other groups are, and they've reached out, and there are people who are working a lot on just the explainability and getting more consistent results. And I think that's going to be exciting work that, people reached out and said, maybe we can think about explainability. And I'm hopeful that we'll find some interesting results down the line. But that's just said, these are so random, we couldn't really figure out what was going on. The same for mammograms and the cervical spine image. Joshua Cohen, who was a postdoc in Stanford, had worked for his postdoc on this concept of gift-splanation. And if you think about just stacking all images together and understanding their their latent embeddings, and then trying to figure out are there differences, is maybe my too simplistic description of his work. And this is from an Asian patient, Black and white patient. And you could start to see, well, maybe the shoulders are the ones that are moving the most here. And the same thing in here. And also in here, that could be the shoulders that accounts for the differences, why the model is able to tell the difference. And yeah, so in our own observations, we may think some races have maybe more muscular or something like that. But this wouldn't explain why the same finding would happen in the hand or on a mammogram. And so we didn't think that this was sufficient. And so if I look at some of the other experiments we worked on, is this, I said that the saliency maps are not very good, but we do know that that's where the model still thinks the highest probability is. So here we can see this is an area around the lung. And what we did here was, what if we masked the highest area of prediction? Would the model lose, its predictive value? And yeah, we see a drop, but it's still better than the radiologists. And so this was telling us that there's still some signal in other parts of the lungs. And we started doing this experiment where we split the chest X-ray into 9 segments. And one thing is just block the patch and use the other parts for training. So you could think about it, just this as a different type of masking. And the other way is just pick one patch, zoom it in, and use that patch for prediction. And when we pick, do the single patch training, the performance of the model is 0.90. And when we block one area, the area that we see quite a drop in is, this area where this area here, which is around sort of like the subxiphoid area. And we know that can be very positional and change. That was what we attributed this. That's why there was a big drop, but we still see a little better than the radiologists. Then we segmented the lungs, and we've subsequently made this data set available, this segmentation through PhysioNet. And so we have these lung segmentations and looked at where does the lung non-lung segment, what's the contribution of the lung non-lung segments and the lung segment. And this was the original prediction. And you can see in the lung segments, we have lower prediction. So, but it's still not in the random of 0.5. And in the non-lung segments, we have these predictions that are higher. And so we can't really say that it's the soft tissues, although that's been like one of the bigger hypotheses we had. So then we started changing the quality of the images. You can see this is a noisy image and this is a blood image. And within blood image, we have, something, especially for the Asian population. I do have to say that some of the data sets don't have a big representation unless you're looking at one from the West Coast, so the Czech expert data set. And here we see a prediction of around 0.59. So a little lower, more lower when it's blood, but still some signal when it's noisy. And well, this may not be the most concerning, but there's a text photo data set, and this was done for low and middle income resource settings, specifically to look at can we look at when we send pictures through WhatsApp, do we have the same diagnostic quality? And in those times, what it does is just taking a picture of a picture. So this is a picture taken with a Nokia phone, or and what we observe is that the text photo predictions, which honestly are a little bizarre and surprising, are actually very good. Like, because you'd think that it's maybe that we're not looking at the primary acquisition data, and this data has been processed. And so this processing is maybe where the signal is coming in, but the text photo and also the digital hand atlas, which is acquired the same way, we see good performance, and we know that that's not we started downgrading the images. Usually we are feeding around 512 for our algorithm training. You can see this is a 4x4 image, very pixelated, and the performance is still better than radiologists. Here it's 0.63. You can see that you're even in the 0.8 when you're at a 40x40 resolution. And so I think this is one of the big takeaways of our work, that if you use TikTok, or you have someone who uses TikTok, you can put filters in front of your image to make it look different. And we did the same by applying low pass filters, looking at gross textural areas and also fine-grained features. So we applied both low pass filters and high pass filters. And this is a chest X-ray, and it's barely perceptible, honestly, when you look at it this way. But the performance here is still almost above 0.85. This for me is the most concerning, because when you show me this picture, I'll just say this is a great picture. And to start to say that this type of information are embedded, I think demands that we look at them and understand what their significance are. And so subsequently, one France looked at, what about how can you mitigate this? And they looked at it by trying to figure out some, augmentation. And so you can see that these are images that are rotated, and then the shear transformation, and then the scaling and fisheye distortions. And honestly, these are sort of like the results of the manipulation, and most of them were low to medium, that, we couldn't really figure out that this is something, that this is the explanation for this finding. Now, one of the bigger comments and feedbacks that we had was that, well, maybe it's because it's your specific hospital and your specific equipment. And would this be unreasonable to think about? Absolutely not. Because, for example, if you have a patient with a high BMI, there may be some scanners that they cannot get scanned on. Or if you have a clinic that's close to an area, let's say a diabetic clinic, then most of those patients may end up, getting scanned somewhere like that. So those patterns kind of healthcare system, especially in an inpatient setup. And so what we did was to pick only images that were done on hospital system uses Carestream, portable chest X-rays, look at AP images, and this were 55,000 images. And then we looked at what's the performance, and you can see it's around above 0.9. And then we picked that same model and then tested it. We're in a network where we have 11 hospitals in the Emory healthcare system, and also that, we also have GE equipment. And so we tested the same train model, what would be like a clean model with other places. And we see it's still the performance, I would say, is good. And, it's not an equipment difference. Worked with our physicists, and if this is an area, honestly, that we need to work on better. And this is a phantom. This phantom we acquired, we had the physicists provide feedback and say, okay, you should acquire these images at, these sequences, these are all the protocols we use, and then use these images for prediction. And what was surprising to me, because I expected that this pattern would come, very random here, like the radiologists, right? It would be neither black or white. We see the same image. So when you're looking at an axial cut of a CT of a phantom, that on some slices, the model is very confident that these are black. And on the other slices, the model is very confident that these are white. Now, I will tell you that phantom images are very, very, very difficult to obtain. And so as a data scientist, this is an area that of gap, and can really inform how we think about AI validation. And so this work is still also like a work in progress. So then we start looking at, pixel brightness. As you can see, we are in this phase for, modifying the images. And if you're a radiologist, you know that, you can change the windows. Now, it may not be something that you do, for example, for your chest X-rays. You may have the Clahi images, which is like that very sharp inverted image. And here we started modifying, could you look at normal? What would be the air? What would be the bone? And we found this is where we'd expect it to be random, not different. It's not because of different pixel intensities. And in this case, one thing we were thinking around is trying to elucidate bone. And I want to talk about bone because I believe that in our experiments, this is an area that we haven't completed. And there are some better libraries that help you remove all the bony structures. But I would say that, some hypotheses and feedback that we've gotten was that bone is everywhere and it's so dense that maybe that signal persists, and maybe that's the difference. I will comment on the phantom. The phantom that we use is a more newer generation one. It doesn't use real human bones. It uses 3D printed bones. So, that may be different data, but we did not find a difference that this is a bone signal. But I just want to acknowledge that there is a limitation, and that is an open area of research. So one of my PhD students, then really further explored these pixel level differences. This work was presented this year at the SIM annual meeting, which, if you're a imaging geek, this is really where you make fantastic friends. So I encourage you to go there. And although there's, like some differences, we were trying to see, at the pixel level, do we find differences between the different races? And we use very traditional machine learning approaches to look at the results here. And what we were trying to do here is also, you can see, like, if you can change the pixel of interest by even just narrowing down to just look at just the soft tissues, or, and that manipulation, I think, was interesting for us to explore. And what we saw was that like ANOVA and MANOVA results, that there was a significant relationship between the intensity of the pixels and the self-reported race. And we were thinking this along the lines for explainability, and when we looked at the machine learning, it was really great in boosted trees. I think if you've worked on any traditional machine learning, I feel like this is the model that performs best for most things. Achieved an AUC of 77.26, showing that at the pixel level, which maybe explains why when you modify all these images, we find that we still can, there's some race information that and that it will likely persist when the imaging structures are removed. So, you don't want to publish a paper and then, someone says, hey, shuffle the labels. I mean, what happens with that? And you can see we took a sample data set. It was like the distribution of the race. Most of these data sets do not have a lot of Asian and African Americans. And when we started shuffling their labels, we see what we expect, which is randomness. And I talked about the confounders. We use this in isolation and as a combination, and looking at BMI, looking at breast density, combining breast density and age, looking at patients who only just have normal chest x-rays because maybe the model is learning that Black patients have heart disease and so they have pacemakers, and just looking, I described a little bit about the bone density features, and also maybe just looking at maybe the race prediction is better when the model is looking at older patients. And what I can tell you after many of these experiments is that this was not the reason. So we did experiment a little bit on, we haven't published this work here, on transfer learning. And, in the interim that that there has been an ImageNet, which is called RAD ImageNet, which is the, the radiology equivalent. And people really do think that will help better in terms of our models. We have, our group is still waiting for access for the data to try and figure out if that works. But if you either initialize your weights randomly or you initialize with the ImageNet weights, and when you initialize with the ImageNet weights, which we usually do to save time, then we do find that those models are able to transfer or perform better for the race signal. And so what was interesting actually is this pre-processing task. For example, when you maybe say an AP-PA detection or a label detection, that for those tasks, actually the race features were not learned well. Again, we'll still come back to the same thing. Very difficult to explain these AI models, but I thought that this was interesting because we do apply a lot of AI in these pre-processing tasks. And it also matters for what task that you're doing. So the best performing pathologies were cardiomegaly, edema, effusion, and support devices versus enlarged cardiomediastinum, fractures, and pneumonia, which have transferred this learning to race detection less. So all those things are just to tell you that we showed that we have superhuman performance of detection of self-reported race on medical images across modalities, multiple modalities and external data sets. And this assessment is not due to anatomic or phenotypic confounders. And unfortunately, after investigating many mechanisms, which I showed like this type of picture here, after applying a high-pass filter, we cannot explain why, and I believe that this requires more attention. So this concept that we can still identify race on these two images is what I describe as these hidden features. And it's not, actually there's quite a lot of work, and this is why I'm going to shift this talk to focus on those new types of work to show what other people are doing, and still the same ultimate discussion will be, we don't know why this matters, and the explainability. And so this is an example work done by Emma Pearson. Osteoarthritis is a disease that is graded using the Kellgren-Lawrence score, which is was learned from white males. And so, osteoarthritis, it has an impact because if people don't think you have severe osteoarthritis, then they're not going to approve you for insurance. And so then that can be quite challenging. And so what this group did is that they developed an AI algorithm, a convolutional neural network that learned from the patient's pain symptoms. So it wasn't just saying this is the grade of severity, but it correlated to the patient pain symptoms and was able to demonstrate that they can narrow the pain disparity based for Black and Hispanics, for low-income earners, and for people with low education. And not only did they narrow the disparities, they improved the eligibility for knee replacement surgery. So again, it's a fantastic study. And we subsequently, after our work, we came back and said, okay, let's look at this NIH data set. Does it learn the race of the patient? And you can see here that we have pretty good performance. And so the question that I would pose to you, and is something that we still have like the sore one, is to think that, well, is this great performance because the models are learning this signal for race, or its inherent signal? And it's okay if they're running the signal for race and this turns out that is important to narrow disparities. But what if you've encountered groups that identify as mixed race, or in Africa where you have still, you can't treat a whole group as just a homogeneous group? And so this is an open research question. Let me show you a different example, which is around breast cancer outcomes, a disease that affects minorities, Hispanics and Blacks worse. They are more likely to have invasive disease at a younger age and usually die young. And so these are some examples. Nancy in 2004, in 1 year before this, she had learned that she had breast cancer, had been very faithful to getting her annual mammograms. She had dense breasts. Unfortunately, when she had her mammogram, it was read as normal. 6 weeks later, felt a lump, went back to the doctor. Mammogram was normal, but with a diagnostic workup, ended up getting an ultrasound and had stage 3 breast cancer, completely devastated. And so subsequently, we know that breast density has been included as a risk for breast cancer, but we see this model and we have participated in validating this. And even if these pictures that show that, hey, there's breast cancer here, this is not how this model works. It just gives you a 3 and 5 year risk of breast cancer, and just feeds the images and encodes them unilaterally and then aggregates those encodings. And if you have the clinical information, then it incorporates that to tell you what's the risk of 3 and 5 year risk of breast cancer. And if you're in the breast space, then you know these models, but these risk prediction models require a lot of information. You have to know the age, the ethnicity, prior breast history, family history. For someone like myself, I wouldn't understand that, and so image-based breast cancer risk prediction model that works well is actually a game changer. And when we look at the performance of this model compared to the traditional clinical models, even for whites and Blacks, is actually better. These clinical models usually, this is for the general population, 0.64, and even lower for Blacks and Hispanics. Again, just like the knee example, why do we have this amazing performance? And, is it because of the race information, or how are you able to just look at a mammogram and say, yeah, Judy, your risk of breast cancer in 3 years is, wherever it is. Here's a different type of work that we did looking at chest x-rays. And these many words here, I just tell you that when you're missing a code is a concern for health disparities. For example, if you say I don't have congestive heart failure and in the electronic medical record. And so as we move to more value-based care, we have these bundled codes, like diabetes with acute complications or chronic complications or without complications. And so what we did here was to pick 6 HCC, those type of codes, value-based codes, and start to say, okay, why don't you predict these codes from the chest x-ray and train a convolutional neural network? As you can see here, let me move something here. Yeah, so as you can see from here, is you start to see the like congestive heart failure. This is a code, and the model is looking around the heart. Again, with atrial fibrillation around the same place, morbid obesity, looking at, also the subcutaneous tissues. You can see vascular disease looking around at the aortic arch, and diabetes looking around the mediastinum and the subcutaneous tissues. And what we show here is actually that we link with one more information, which is the social deprivation index, which is a marker for social determinants for health at a very, very granular level. We'll tell you the poverty levels, what's the education level, what's the nearest store, very granular. And we include this looking at our population, which had an average age of 48, but very high social deprivation index of 45 compared to our white population who had a better social deprivation index. And in this our prediction, we find that we are around 0.7 to tell you that there's a missing code from a chest X-ray. And if you think about something like this in application, if you've had to use the translations in the healthcare system, the computer that comes around and someone tries to translate for you, it's very exhausting. And if you have to see many patients, you're not going to spend an hour trying to collect, other types of history beyond what you need. And so it's not unusual. Then you can see that in this case, we have a 65-year-old self-reported Spanish-speaking woman, COVID positive, without a diagnosis for congestive heart failure, was labeled by the model to have congestive heart failure, and on chart review had an echo, had diabetes and an echo, and an order for an echo, but was never performed, and lived in a social deprivation index area of 45. So I started showing, we have this risk. Fine, we started our work with self-reported risk, moved on to these diagnostic, decision support tools, either osteoarthritis or breast cancer risk. And now we're moving in to just say, I'm not just telling you the disease that you have, but I can tell you what area you're coming from, just embedded on an imaging. And I mean, if that doesn't surprise you, then you really need a little more inspiration, because for sure it does surprise our group. And so with these next studies are along the same way. So it no longer tells you that this is where Judy lives, but it tells me what my future healthcare expenses of patients on chest radiographs are. And I believe this can be actually a very slippery slope. And in this work, they looked at 3 and 5 year future expenses. You can see for the first year, the ROC is 0.81 and drops down to 0.77. But here is why this type of work matters, because when you need disability, they'll send a nurse to your room, to your house, and draw blood samples, and then the underwriting process, quite a laborious process. But if these models are embedding this type of information, and I do not want to say that this information is always reliable, then you can imagine a scenario where I would just have a chest X-ray of you and tell you where you live, where your healthcare expenses are, what your ICD codes are, and really potential for, I think, misuse, in my opinion. And so these are examples. They show some, good examples. This is someone, I would say that this is a normal chest X-ray. The bones look young. This is probably a young patient, so they incur cheaper costs. This is someone with a port. I know the saliency map I described is quite off, but we know if you have a port, you probably either have cancer or are requiring some more medical care. So the examples they used here are, in my opinion, pretty straightforward. They give some where there were bad predictions. You can see this, there's some opacities here. And this was actually predicted that it would be very expensive, but ended up being cheap. And this image here, which, apart from an ectatic aorta, is a normal chest X-ray in terms of no acute finding, then this was predicted that it would be lower, but ended up getting higher expenses. And so along the same way, this group, what they did was look at biologic age. And this is not unusual. You look at the bones of a patient or the arteries of a patient, and you hear they're 90, and you're like, wow, what have they been eating all their life, And so we're looking at chest X-rays, looking at this chronologic age, which is just the date of birth minus the current date, and this biologic age, which is thought to have cumulative effect that maybe some patients age older than others. And so again, trained a convolution on neural network, and we would output the chest X-ray age, and then they would compare what was the chronologic age and then what was the observed outcome. And here are some examples. These are people who had chest X-ray age greater than the chronologic age, which means they're aging faster. And these patients, you can see all these examples died. And these patients who are aging slower, they ended up alive at the time of follow-up. And so this, that you can tell now the healthcare costs, the codes, and how you're aging, again, still coming from these chest X-rays in an ability that radiologists cannot present. I discussed some of the potential downstream harms that can be used for this from these algorithms. And so can we harness these hidden signals? I started by discussing that there's widespread use of imaging, and there is some biomarkers, and especially when we start to think about merging multimodal data sets, and they rely less on human curation, and in that way can be cost effective, especially as we start to see radiation doses come down. And, based on our work, we were approached by many people, including detectives, saying, hey, what if we harness your ability to help us, with forensic pathology, especially in mass disasters where it may be difficult to identify patients, or in clinical trials where we may be missing some information and would like to understand what was the outcome for a specific group. I did mention this sort of opportunistic screening. And my answer is yes, but we do need to understand why and when it matters. And so to do this, then we have to look at some of the trends that can be amplified and learned by the algorithms. One, we know that Black, Hispanic, and non-white patients are less likely to undergo diagnostic imaging in the ED. So you could completely be missing a data set. The Emory team, maybe 2 or 3 weeks ago, published this paper in the New England Journal of Medicine that is saying that if you're Black, it doesn't matter your education or finance level, you're less likely to get resuscitative CPR in the field if you collapse. And if you think about that, then if most of those patients are dying outside, when you're looking to build your model on the patients who got imaging or who got to the hospital, you could really have a big blind side. And some of the hospitals, for example, US minorities having hospitals, or patients who are cared for like cirrhosis in a specific hospital, these patterns can really be amplified in the data as you can see the potential. So to maybe harness this, we still need to think about explainability, and this remains a big challenge. But the interesting thing about working in this sort of open, this type of open field is that a lot of people have reached out on explainability, and I think it's going to be an interesting space for us in radiology as we think about computer vision. And then we do need to think about, we don't have still the right data sets, and if sometimes we don't even have the correct labels. And so this group looked at, observed maybe around 4% of the data sets have race labels. And this study here was just trying to say, okay, how many Black patients or how many females do you need in your data set? And this is a gray area that we still cannot understand. And so I'll end by saying that, there are no simple fixes for ethical AI in healthcare. It all is a spectrum, and we call ourselves the AI Ventures Group. We think about problem selection, data collection, how to define outcomes, and then the algorithmic development and post-deployment considerations, because you have to require diverse data and diverse teams to really work on ethical issues in AI, in AI in health. And if this is an area of interest, we really do have a very vibrant group that discusses these problems and gets feedback on each other. So please reach out to me. Kathy, I really appreciate the time. I know that I am out of time, but I would say that my work in Africa, one of the big takeaways is that this is the beginning of doing research and data science in this new way of the cloud and away from paper on the continent. And it presents such a great opportunity to leapfrog. And one of the recent examples I've been giving is, in 2016, Geoff Hinton said, let's stop training radiologists. And luckily, a lot of people, including you, came up and said, look, this is false. We need to keep the course. And now what we are seeing is that, I think in September in radiology, there was another paper that said, let's stop training radiologists. And it was in response to tuberculosis diagnosis, because we had this paper that was published earlier this year that looked at what's the sensitivity of AI for tuberculosis screening, and reported that it outperformed the radiologist, and the WHO subsequently gave a mandate that AI could be the first line for tuberculosis screening. Just that statement, if you think about the implications of government of where financing goes. And this is an area where most of these algorithms tend to be private, they're black boxes. It tells me that we do really need to work together, because these problems cannot be solved with one person. And I think we have potential to cause harm if we keep holding on to data. And so that was one of the big messages, and getting people to work together. Again, I appreciate the invitation, and I hope that I maybe challenge you to think differently around this topic.
Oh, thank you, Judy. Thank you, Dr. Gichoya. What a fabulous, fabulous tour de force talk there with all the experiments you did. I mean, I guess even though we don't understand completely why you are able to determine race from medical images, at least it warns us that we need to be aware of bias and do our best to mitigate that, at least by good data cohort design. I thought it was interesting. You looked at everything all the way down to the instrumentation as well. Really fascinating work, and fascinating work that you're doing. You know, I think that's one of the wonderful hopes, is that we can use these technologies in underserved areas as well. So thank you for all you're doing to move these technologies forward, and all the work that you do in Africa as well as in this country. Fantastic. We do have a question in the chat here. If let me just go ahead and read. It says, it seems there's a confliction between the results of original and lung only. This is back when you were describing your original experiments where you segmented out the lung. It said the attention slide shows that the model predicts based on the lung area of the original image. However, the AUC drops from 0.9 to 0.7 when only the lung profile is used as input. Can you provide any thoughts on this?
I just think it's because the attention maps, the saliency maps are wrong.
Yeah. Okay. Yeah. And we've seen that.
That's my only, yeah, I think this is just because I think, like I mentioned, I just put here just, you know, because people be like, did you look at saliency maps? Yes, we studied this map so many times, multiple hundreds of images. We couldn't see a pattern. And so I think that's, you know, that's the incorrect part more than, you know, that if correlating these two, but that's a great question.
Mm-hmm. And how do you suggest, I mean, how do we go about doing our best to at least have consciously try to mitigate the bias, at least in the development of our models? What are some of the things that we can do to make that less of an issue, which is really garbage in, garbage out? If we start and do that part wrong, the rest of it is going to be wrong.
Yeah, I think, you know, really, and I'm glad that this series is called Data Science, not AI, even if I ended up talking about this a lot. And the reason for that is people really underestimate what it takes to curate a good data set. This work made us develop a lot of data sets. And so, for example, the Emory Embed data set, which is quite a big data set, is, you know, it's, if anyone is trying to do mammograms, you know, you can just search on it online. We learned so much. It takes around 2 years for our team, 2 years of full-time work to develop a data set. And so the problem is, one is that people always assume that these myths, and I think that's where maybe that's the low-hanging fruit, that, oh, but I have 5 Black patients, or, oh, but I didn't include Black patients, you know, so my model cannot be biased, or I didn't include female patients. And so people think that just because you included or excluded, that's enough to think, you know, to solve bias, and that's incorrect. And then the second area, then subsequently people may not do this subgroup analysis. So I would say that you don't just look at, for example, women tend to generally be, you know, minorities, but when you look at Black and Hispanic women versus white women, they're different. And so this intersection of multiple factors when it comes to think about disparities. And so, but we don't understand if it's just these protected classes or it means it's the same for other classes. And so I think we still need a lot of work there. What I would say is that to do this work, you cannot do alone. You require a lot of people who are just bringing new perspectives to your work. And that's really like forming diverse teams. We need incentives to align other people who hold a ton of better data that would allow us to look at that granularity. For example, insurance providers who are buying and purchasing information from, who's overdosed in what area, that type of granular information, buying your credit card information and linking it to their data set. And myself and or Kathy will never be able to have this type of data set. And so we also need to think about incentives on how we share these new types of data. And then the most important thing is to really not take it personally, because I think when no one wants to be told, oh, Judy, you're biased, or, you're racist, and this is just work, it just really is work. All of us, I can say, enjoy tackling health disparities and healthcare problems using data sets. And so if you start to attack people, then they sort of withdraw. But as we start to see the NIH mandate for more people to release their data sets, I mean, when you're a data scientist, you're going to start to pick up these problems, and we don't want to get to a point where we are shaming people and say, oh, Emory, they think they're very diverse, but they're racist or something like that, because then this work is going to stop.
Yes, no, it's very important work to carry on. And, sometimes we just don't even have access to that information. Oftentimes we have to dig very, very deep in unrelated records to find things like, education level and socioeconomic factors. And sometimes even just the fact of race is not easily gained from it. One last question here. What do you think about data synthesis? Does that have a role to play in what we are doing?
So actually, we're just finishing a lot of experiments on, you're talking about synthetic data, correct?
Yes.
Yeah, it's a slippery slope. And so I can tell you that in our experiments, which was also very surprising, is that now most of the models, when you use like the GANs, they assume that you're white.
Interesting.
And that information perpetuates.
Very interesting. Well, this is a conversation to be continued with Dr. Gichoya. We'll have to have you back again soon. Thank you so much for sharing this wonderful work and continuing it. And when Judy says, please join the teams and work together, she really means it. So if you're interested in this kind of work, go ahead and get involved with her. Judy, thank you so much.
Thank you again for the invitation.
Wonderful, wonderful presentation. Thank you. Bye all. We'll see you next month.